Hello, everyone. My name is Angelo Caravano from the University of Munich in Germany, and I'm going to tell you today about my work on lattice simulations of Axion inflation. If you want to know more details, you can find them in this paper that I write here with archive number in case you're interested in knowing a bit more. So let me start by doing a very brief introduction to inflation. But you probably all know this. Inflation is an accelerated expansion of the early universe that was originally introduced to solve for the horizon and flatness problems of cosmology. And in the standard picture, this accelerated expansion is driven by a scalar field, a so-called inflaton field. And if the universe is filled by a background value of the scalar field that is the same everywhere and constant in time, we can achieve an accelerated expansion if the potential of this field is flat enough, the so-called slow-roll condition. Now, the reason we like scalar field model of inflation is not only because it can provide us a way to accelerate the expansion of the universe, but it can also, it gives us a very natural way to understand why there are perturbations in the early universe that we can, for example, observe in the cosmic microwave background. These perturbations in the model are seen as quantum fluctuations of the scalar field, because if this field is quantum field, it cannot be perfectly homogeneous. It has to have some fluctuations, and these fluctuations, what we know from these quantum fluctuations, matches very well what is observed in the sky, and that's why we really like the scalar field model of inflation. Now, to really understand my work, we have to go beyond the single field model of inflation. And there are many reasons to do that. And I'm going to give you a phenomenological perspective on why it is interesting to do that. So let us say for a moment that together with the inflaton, during inflation, there is also some gauge field that, for example, can be a U1 gauge field, which is equivalent to the electromagnetic field of the standard model. And let's assume that this gauge field has an interaction with the inflaton field during inflation. For example, an interaction of this term, the so-called Chern-Simons interaction. Now, this model is known as Axion model of inflation, and in particular Axion U1, because the gauge field is a U1 field. But all it is just having a scalar, some gauge field that has this interaction with the inflaton. Now, thanks to this interaction, there are some observational consequences, because making the long story short, if this interaction is present during inflation, there will be an exponential production of gauge field particles induced by the background. So the inflaton background is gonna, thanks to this interaction, is gonna induce an abundant production of electromagnetic field. And then when this electromagnetic field is produced, it's going to decay back into inflationary perturbation, delta phi, into the perturbations of the inflaton, which, as we're discussing in the last slide, is what we observe. So it means that if this was the model of inflation, we can actually look at our observables, like the cosmic microwave background and Alaska structure, to try to hunt for the signatures in this delta phi. So now we understand why we want to go beyond the single field model of inflation, because we might be able to probe this kind of interaction by looking at the sky. Now, understanding the shape of this delta phi has been one of the purposes of my work, and I'm going to tell you more about that. But let me start by giving you some known results about what do we know about how the scalar fluctuations in this model are affected. So the power spectrum of the curvature perturbation, which is more or less density fluctuations, or are related to density fluctuations, are going to be the sum of two pieces in this model. The first is the vacuum piece, which is the usual vacuum fluctuations, quantum fluctuations of the inflaton field. And the second piece is the source piece that comes from this inverse decay from the interaction of the gauge field. And you don't really have to remember the explicit form. Actually, it's very simple. You have to remember that it is exponentially sensitive to this parameter, which is proportional to the inflaton derivative. Now, this in electromagnetic field interaction with the electromagnetic field also induces some non-Gaussianity, because all interactions during inflation give us some non-Gaussianity. And this non-Gaussianity is peaking on equilateral shapes, so that's not so relevant for us. And it's also exponentially sensitive to this parameter xi. And this results were obtained assuming a constant xi. That is something we're going to talk about later. Now, you can see here that these two pieces, the second piece typically grows in time, and that's a very nice characteristic of this model. And this grows in time because it's exponentially sensitive to this parameter, phi dot, that is proportional to phi dot and inversely proportional to h. So this sourced piece will grow in time. So in inflation, you typically have this following situation. We will have an early phase, which can be, for example, a CMB, relevant for CMB experiments, where we are in a situation of vacuum domination, where when the fluctuations, your scalar fluctuations are dominated by the vacuum part. And then at some point during inflation, inevitably, because at some point phi dot has to fall down the potential, inevitably the source part is going to win, and we're going to end up in a case of source domination. The exact time and how this happens will depend on the particular inflationary potential, but it's inevitably that's going to happen. And now, when fluctuations grow in this phase, we typically go into a situation where fluctuations become large and that the model loses perturbative control. And this means that we need to study, we need to find some other tool to study what happens to this model that is not based on perturbation theory. And this part is very interesting because having large scalar fluctuations can be very, very interesting for generating, for example, primordial black holes and gravitational waves. And this model is a very natural way to generate those effects. Now, let me just specify for a second, what do I mean by nonlinear phase there? The first thing that happens is that if we look at the equation of motion for the inflaton field, how it moves on its background, the slow roll motion, at some point, what happens is that the gauge field is going to be so large that it cannot be neglected anymore in determining how the inflaton background is moving along the potential. And this is typically called backreaction. And you can see by this equation that it can be seen more or less as some sort of extra friction that is added to the Hubble friction, but it's not so simple, as we will see later. So now, to solve this problem, I'm going to employ what's so-called lattice simulations. Lattice simulations are a numerical tool that has been developed to study, and that has been quite used in early universe physics to study the reheating phase of the universe. And here I'm going to show you just some example. But basically, our purpose was to try to understand how this lattice simulation could be used to understand not only the reheating phase of the universe, but what kind of simulation can teach us about inflationary phase itself. And in this talk, we're going to focus on the Axion U1 model, but I want you to keep in mind that during this talk, I want you to think of the Axion model of inflation that I presented as an example of what this kind of simulation can do during inflation. Now, just very briefly, how the lattice approach works is that instead of solving the system perturbatively, what we do is that we discretize the inflationary spacetime, and to each point of the spacetime, we associate field values, both for the field and for all your fields that you have in your model, and then you solve the full nonlinear equations of motion across all space points. Using the fully nonlinear equation of motion, solving them numerically. That's very, very briefly. These are the equations look like in this model. You don't have to remember this equation. There's just one equation for the scalar field and some equations for gauge field components. Now, the way it works in practice is that we take a little patch of the inflationary universe that it's at the time we start the simulation is smaller than the Hubble horizon at that time. So we can initiate the Bunch-Davies vacuum fluctuations, assuming a flat spacetime in this box. Then we use these equations of motion, the nonlinear equation of motion, and to evolve this box until it becomes super horizon. Now you see here that the box remains the same because we use co-moving coordinates, and it's the Hubble sphere that is shrinking. And at the end of the simulation, we're going to end up with a super horizon simulation. And this is going to stay frozen like that until the end of inflation in terms of scalar curvature perturbation. So we can now take this as a picture of the universe at the end of inflation, and we can look at its statistical properties. That's more or less how it works. And now I'm going to show you the results of the simulation. I'm going to divide them into two parts. First, I'm going to tell you about large-scale results, which are pertinent to having, which are basically is the case where we have a small xi and we are in the perturbative regime of the theory. And then I'm going to tell you about the small-scale results where xi is large and perturbation theory doesn't work. Now, the first thing, of course, that we need to check is that if we look at this final box in the linear regime of the theory, all our results agree with all the perturbative results that have been obtained in the literature. And I'm not gonna spend so much time in that, but the answer is yes. And the power spectrum and bispectrum agree very well with the literature. And although I don't spend too much time on this, just because of lack of time, I want to stress that this is a very non-trivial result. We're very used to place bounds on our observations, but when we do some approximation, like for example, having a constant inflaton velocity that was assumed to obtain this analytical estimate for this power spectrum and bispectrum, we don't know really exactly how our approximation affects the final result. And this simulation is a way in which you can check in the linear regime what is the error induced by the approximation that we make in our analytical computations to really know this error. And I think this is a really important thing to do, to go beyond some first-order analytical approximations. Now, the second thing that we can do, which is actually, I think, the most powerful, is that actually of course, we can compute the power spectrum and bispectrum of this model, but we can do much more than that because we have the full picture of the universe at the end of inflation. We can access the power spectrum, bispectrum, but we have a picture of the universe. So we can, in principle, know much more information. For example, we can plot the histogram of the inflaton value or the scalar perturbation value across all points, and one can really see what non-Gaussianity in this model looks like beyond the some FNL expansion. One can really see what is the non-Gaussianity looks like. This is some histograms on which are the same, just the right one as a logarithmic scale on the y-axis, where one can see that the shape of non-Gaussianity, deviation from non-Gaussianity, is very non-trivial. And this is something that you cannot really see with standard perturbation theory techniques. And to quantify this non-Gaussianity, what we can do, for example, is to take the cumulants of these distributions, normalized by, in a dimensionless way, by the correct power of the standard deviation. And what we see is that if we compute the cumulants of this distribution, we're going to see the value of the cumulant grow with the order. And I think that this is a very puzzling feature to some extent, because it means that there is a really large amount of information contained in high order statistics, which is sort of expected because we see that non-Gaussianity in this model manifests as a sort of tail in the distribution. And this is very interesting because it means that actually when we parameterize this non-Gaussianity as an expansion around the Gaussian distribution in terms of some simple parameterization like FNL, this is not gonna tell you the truth. The non-Gaussianity in this model is much more complicated. And this is a very powerful thing of this, that this stimulation allowed us to discover. And I want to stress that here we're still in the linear regime. Perturbation theory is still valid, and the simulation gives the same result. But we are able to really understand much more what the non-Gaussianity of this model looks like, which can be potentially be very relevant for observational purposes. And I'm happy to discuss about this. So, but of course, I told you that the original purpose was to try to understand what happened in this model beyond perturbation theory. And I'm gonna, in the last few minutes, talk about that. So what we see here on the left plot is what happens to this parameter xi, which is basically the inflaton velocity a bit with some constant and the Hubble scale at the denominator. And you see that, as I told you, in the linear regime, this will be monotonically growing. But on the right-hand side, now I show you the result of what happens when you start your simulation in the linear regime of the theory, and then you wait until this parameter become so large that you exit perturbation theory. And you see that this monotonic behavior is broken, and you see some sort of oscillatory peak here, inflaton velocity, which is the backreaction and how it looks like. And the simulation allows to study what's going on in this regime. Now, this is not new, because it was already known that the backreaction in this model was non-trivial, or it was already guessed by some semi-analytical works. And we confirmed this result by comparing our result to some of these semi-analytical works. Now, let me briefly mention that what we do is to study the transition between linear and nonlinear regime and what is going on there. What happens at the very end of inflation, where the dynamics is very nonlinear, is still an open debate. And you can, for example, check this Lattice work, this recent Lattice work that studies the end of inflation using this similar Lattice techniques, or you can check this paper by Peloso and Sorbo that looked at this non-trivial backreaction in purely analytical way. But what we discovered new, so this kind of non-trivial background behavior, which shows as some sort of resonant peak, is not new. What is new is what we find as a very interesting result, is that when the system enters this nonlinear regime, this nonlinear phase or strong backreaction phase, as soon as the system enters this phase, non-Gaussianity is suppressed. And you can see here by looking at the value of the histograms of the cumulants that I was showing before evolving during the simulation, you can see that you start from a very Gaussian integral, which is the Axion fluctuation. And then at some point you develop some non-Gaussianity, but as soon as you enter the nonlinear phase, Gaussian distribution is restored. And we understand this in terms of the central limit theorem, but this is slightly unintuitive, and it was actually something that is a bit different than what we were expecting by looking at the literature. Because before our study, it was believed that a large value of psi, more gauge field, meant more non-Gaussianity. And this was kind of intuitive, because non-Gaussianity is given by interactions. And this meant that actually, because of this non-Gaussianity and this tail that you have a very efficient production of primordial black hole, because you have a tail in this distribution. And this means that this parameter has to remain small at all times, this psi. And this basically was used to conclude that in this model, you cannot really have very large or observable consequences at the CMB, or for example, gravitational-wave interferometers, because otherwise you're going to produce too many primordial black hole. Well, now, since we proved that this first thing is not really valid, this whole picture needs to be revised, which means that this model can lead, actually, the minimal formulation of this model can lead to very interesting observational consequences at large scales. So let me conclude now, and I told you that we did the first simulation of Axion inflation, and we find out some interesting results that I leave you here. I don't have time to recap them because I run out of time, but I'm gonna be happy to discuss about the results and to take your question. So thank you.